telling us about a new inference algorithm for discrete probabilistic programs. Take it away, Matt.
All right. Hi, everyone. I'm Maddy Bowers, and today I'll be presenting on a new approach to inference in discrete probabilistic programs, which we've implemented in a language called Pluck. So the algorithm I'm going to tell you about today was designed to work with a quite expressive language. So for example, here's a function that generates random binary trees where each node holds a number. And in particular, this uses algebraic data types and discrete random choices, arbitrary recursion, and we support a whole bunch of other features, like higher-order functions as well. Now, when the users define this program, there's a handful of different questions they might ask about it. For example, they can query the distribution of some expression in the language. So for example, here is an expression that samples a tree and then asks if its size is less than 4. And Pluck determines that this expression evaluates to true with probability 85%. Now, a user could also ask for something like the conditional distribution of some expression, given that some user-specified Boolean condition is true. Or, for example, we could generate samples from these conditional distributions. For example, here we condition our program on the condition that generates a valid binary search tree and sample from that distribution. Now, in order to support this kind of user experience, we want to handle this kind of expressive language and ideally provide exact answers when possible, but gracefully fall back on accurate approximations when we can't. And this is a really hard problem. A lot of existing languages have important drawbacks. So for example, exact inference in discrete languages frequently can't handle this kind of recursive tree generation program, which has infinitely many possible executions. And approximate inference algorithms often can't leverage the structure of the programs to actually leverage independence and do this efficiently. So they instead often fall back on like Monte Carlo algorithms that, for instance, would never randomly hit on a balanced, or rather on a valid binary search tree. And so our approach is going to build on a few ideas from the literature to derive a new algorithm that can actually deliver these capabilities. So the first of these ideas is laziness for efficient inference. And this is actually something that has been known for a long time. In fact, going back to some of the earliest probabilistic programming languages, like one developed by Daphne Koller and colleagues in 1997, relied on this insight. But in the past decade or so, laziness has mostly been abandoned in favor of approaches that exploit independence in a program with various static analyses. So in this work, we're going to be revisiting this idea of laziness in light of these recent advances in sophisticated inference. So first, let me show you why laziness can be useful for inference. Say we've written a probabilistic program perturb that takes a string and stochastically inserts typos. So for example, we might run this on the word lazy and get out words like lucky or lousy or hazy. And there are actually infinitely many possible strings that this could produce. Now, as a program, perturb is going to be a recursive function that takes an input string of characters, and either that input is going to be a nil, in which case it's just going to insert any number of characters, or the input's a cons, where we'll decide whether or not to keep that first character, we'll insert some number of characters, and we'll recurse on the tail of our input. Now, these helper functions, maybe keep and maybe insert, essentially do what you would expect. So maybe keep is going to stochastically decide whether or not to drop the first character, and maybe insert is going to stochastically insert a random string in front. And now, given a program like this, a natural question we might ask is, what is the probability of corrupting our string lazy to a particular output string, like lucky. Now, one approach to this is just to enumerate possible paths through our program, right? So for example, at the first step of perturbs recursion, we could keep the L and insert the word, or insert UC, or we could drop the L and insert the entire word, luck. Or we could, for example, drop the L and insert some other prefix, like SE. And continuing this process, we can build up the full 3 layers of the recursion in this example. And if we add up the probabilities of all of the paths that lead to lucky, then we have our answer. But there's an issue here, which is that this tree is actually infinite. And in fact, it's infinite even at the very first level, because we could decide through the recursive maybe insert function to insert a string of any length. Now, so standard enumeration is never going to terminate. But what if we adopt the lazy semantics here? So in the lazy semantics, we're going to thunk our arguments. And so we pass in these unevaluated thunks into our function. And now, with equality being the classic recursive implementation on lists, it's going to first check that the head of the list matches before recursing on the tail. And in particular, this means that as soon as a character doesn't match, we're just going to immediately return and not do this recursion on the thunk representing the rest of the string. And this means that laziness is effectively implicitly marginalizing over all of the possible, or all of the choices that are inside of those unevaluated thunks. They simply aren't part of the possible execution paths when you're viewing this lazily. And this is great. So for example, on this particular program, it actually brings us from an infinite tree down to a finite tree, because we're going to end up rejecting every execution path that has an incorrect prefix as soon as it produces the first incorrect letter of that prefix. And so this is great, but we actually still have an exponentially large tree of executions here. And the key issue is that we're running into a lot of the same subproblems, the same subtrees, again and again. So, and we'd really like to kind of merge these, which corresponds to exploiting the independent structure that's present in the probabilistic program, right? So there are multiple ways to get to the same intermediate state, and we really want those to not be fully represented again and again everywhere they show up. Now, this kind of structure is exactly what modern efficient discrete inference algorithms focus on. And in particular, we're going to be looking at one called knowledge compilation, a state-of-the-art technique for inference in discrete probabilistic programs. Now, this works by compositionally translating a probabilistic program into a representation of all the paths. And importantly, this representation is a graph that can capture exactly what we were looking for on the previous slide in the perturb example, where since it's a graph, intermediate states can be reached by multiple incoming paths. But standard knowledge compilation is strict. So for example, in something like let x equals E1 and E2, we're first going to compile E1, compile E2, and then combine these representations to get our overall expression compilation. And the same goes for function calls. So with something like equal perturb lazy lucky, we are going to attempt to compile our argument and end up just failing to terminate, because there are infinitely many ways that perturb lazy can execute. And so our approach is going to combine the benefits of laziness with these modern techniques of knowledge compilation. We're going to do this by making knowledge compilation lazy. So how do we do that? Well, when presented with an expression like this, we can thunk E1 and then go and compile E2, just compiling E1 on an as-needed basis if E2 ends up using it. And we can do this for functions and constructors. And with perturb, this means that we're going to thunk our arguments, so we won't attempt to do that big compilation up front. But there's a little bit more nuance to making this actually work in practice. So let's look at a simpler example. So here's a program that, in its first step, generates a list x's, which is a random number of random Booleans. And in the second step, it checks if every Boolean in this list is true. Finally, and finally it checks the length of this string, and if it is small, less than 4, then we end up returning B, otherwise false. And here we're going to end up thunking x's and B, and when we get to this point in the program, we're going to end up forcing B, right? And if we just forced exactly what we thunked up there, then we would be out of luck. We would be attempting again to generate that infinitely large distribution. But here, we can actually leverage the fact that we have this path condition, right? And using this, knowing that x is only going to be a short list, we can compile conditionally, or rather, we can compile the conditional distribution of B, conditioned on our path condition. So, and this, in general, is the key benefit of lazy compilation. So we're allowed to compile these conditional distributions of thunks, which can be a lot simpler than the full distribution. So in this case, it actually brings us from an infinite situation to a finite one. Now, there are actually some issues that come up with this when it comes to caching, because if the same thunk appears in multiple different path conditions, you don't want to have to compile it in every case, but you can't always reuse the same compilation result across every usage, depending on the path condition. So details of that are in the paper. We developed a technique called guarded caching to handle it. Now, one place where this kind of compilation is super useful is when dealing with compound data structures. So this is a very common pattern in probabilistic modeling where you have some observed structured data, and you have some model of your data that you can sample from, and you can check if these results are equal in order to see how likely your data is under the model. And in strict knowledge compilation, when we're trying to generate this structure representing all the ways that x could go, we have to end up representing full distributions for each of the elements of this list. And in particular, and these are really complicated distributions at times that have to encode dependencies between all these different elements. Now, for example, if we focus on x3, so in general, this is the situation with strict compilation, but with lazy compilation, we can actually do something a bit smarter. So when it comes to compiling x3, we actually know that equality has already checked that the first two elements were equal to their observations, right? So essentially, we get this path condition that tells us that x is 1 is 1, x is 2 is 3, and this can give us a much simpler distribution than we would have otherwise. And so, so what does this all buy us? Well, we've implemented lazy knowledge compilation in Julia in an open source language called Pluck, and we'll compare it to Alia, a Julia implementation of strict knowledge compilation based on the DICE language. Now, the first question that we're going to ask is, how do these approaches compare on classic benchmarks from the literature? So here's a log scale graph showing the ratio of runtimes of Pluck to Alia. So anything above the dotted line is Pluck doing better, and below is Alia. And first, we note that, there's a handful of programs where you can't take advantage of laziness, and so you're just going to get some overhead from the lazy approach. And in particular, on that first benchmark is the most dramatic one. We're around 28 times slower. This one is sort of a worst case for Pluck, where it's a big Bayes net, where the same thunks have to be forced across many different disjoint branches with disjoint path conditions. And so you end up having to do a lot of recompilation. Now, there are some benchmarks where there's minor benefit of laziness, and here we see some improvements of Pluck over Alia. But where laziness really shines is on these models of structured data, things like the perturb example from the start, probabilistic context-free grammars, generating sorted lists. In these situations, we end up going from taking, Alia takes seconds to around a minute, and Pluck finishes in milliseconds. So it ends up being around 1,000 to 10,000 times faster. OK, so let's take a closer look at this scaling. Let's look at how we scale with respect to the size of the observations. Now, first, we find that there are some regimes where laziness is really key to scaling. So on this log-log plot of input size versus time versus input size, Alia scales exponentially, while Pluck and lazy enumeration scale polynomially. And conversely, there are other places where the independent structure that you can get with knowledge compilation, or that you can exploit with knowledge compilation, matters a lot. So here, lazy enumeration is not going to do well. It'll be exponential, and Pluck and Alia are similar polynomials. So Pluck can take advantage of kind of the best of both of these worlds. Now, additionally, for infinite distributions, on that previous, or in all of our earlier results, we had to, or rather, on the ones that are infinite, we had to give a recursion bound to Alia. And here's a plot of runtime versus recursion bound. And if you set it too low, it'll terminate quickly, but give you a wrong answer. And so we are very careful in this plot, or in our experiments, to set a bound that is just that is just high enough to produce the correct answer. But if you set it too high, you're going to end up scaling. Very poorly with the bound. And in contrast, something like Pluck is effectively inferring the bound for you as you go. You don't need to specify any bound. Laziness effectively, unrolls the recursion just enough. Now, for time, I'm going to skip over some of the rest of these results, but the full results are in the paper. We've also evaluated on randomly generated programs to look at the robustness to different ways of writing Pluck programs. We find that Pluck outperforms Alia. And finally, Pluck is also fast enough to run inside the loop of a program synthesis algorithm and can solve more problems faster than other methods. And again, the paper has full details for those experiments. Now, we've also open sourced an implementation of our algorithm in Julia, which you can check out here, complete with a tutorial, documentation, language reference, developer's guide. And so please try it out and let us know what you think. And additionally, the paper goes into detail on a few other things I couldn't cover in the talk. We have an approximate inference version of our algorithm that works when exact inference is too expensive. And we have a correctness proof based on the semantics of Dash et al. On the theory of lazy probabilistic programming. So find me at the conference. I'd be happy to chat more about any of this, and thank you so much.
we want to take one question maybe? We're running a little bit behind, but yeah, for us.
Thank you for the nice presentation. I was curious, does Pluck ensure that the number of program paths is finite? Does the DSL ensure that? And if not, have you thought about ways you could get maybe upper and lower bounds based on enumerating path probabilities, which is something that people do in the literature? How would that interact with your system? Thanks.
Yeah, thank you. That's a great question. So right now we do not automatically infer. So our DSL is very general and doesn't enforce that you're doing something that terminates. You can have a timeout and exit early, of course, but in the cases where, I'd say there are two things that you can do in the cases where it's not going to terminate. One is that the SMC version, or rather the approximate inference version of the algorithm that I didn't have time to talk about here, can be used in cases where there would be infinitely many executions, at least some of those cases. So that gives you a bit more flexibility. The other thing is, you mentioned the idea of getting bounds, and that's something that we've looked into a bit. We've worked with lazy enumerative approaches that sort of explore the path of traces in a kind of best first way to try to figure out as much of the probability distribution as possible. But I think adapting that kind of thing to work with knowledge compilation is an area that we've thought a bit about but haven't completely figured. We would love to, I'd love to chat more about that later.
Thanks. Let's thank Maddy again.